Hi, I'm an RF applications engineer at Silicon Labs, and I'm going to demonstrate a few RF layout design practices which should be applied during the construction of an ISM band unit. The design tricks mentioned in this video and in our layout design guides, application notes should be carefully followed in order to achieve the best RF performance. This video can be divided into three big parts. In the first section, I am going to speak about the importance of proper RF layout design. The main part of the video is going to show the most important RF layout design practices by providing both an incorrect and a correct design, highlighting the presented design practice. In the last section, I am going to show a layout design where the presented recommendations seem to be more or less implemented, but still, there will be some minor mistakes in the design. First, we should discuss why the proper layout design is important for these units. It is important since it affects the RF performance of the unit. If the layout is designed incorrectly, that can cause degradation in the communication distance, the unit can violate the relevant EMC regulation, and even the battery life can be reduced. At first, one would think that the RF performance is affected by only the layout of the RF section. The position, distance, and orientation of the RF components in the matching network, the routing and dimensions of the RF traces, and of course the used antenna. But beside these, there are a few additional factors such as ground metallization, the routing of non-RF traces, especially the supply lines, and even the substrate parameters, board thickness, dielectric constant, and the number of layers. Furthermore, the other high-speed blocks and converters mounted on the board can cause extra spurs in the RF spectrum or sensitivity degradation. So the filtering and the isolation away of these blocks from the RF part become also important. The most important part of the proper layout design is the RF circuitry itself. The RF transmitter ICs can synthesize high frequency and high power signals at their TX output. Fundamental, its harmonics and additional spurious content. A part of this power is radiated, the other part is dissipated on losses. On the Silicon Labs reference design boards, the function of the TX matching is to drive most of the fundamental power into the antenna, thus to provide the required impedance transformation between the RFIC and the load. Simultaneously, for suppressing harmonics and spurs, a proper filtering network should be used between the matching network and the antenna. The matching and filtering is combined in one series L parallel C ladder structured network, which is also used for the RX side during receive mode. Examples shown in this video are based on a general 2.4 GHz EFR32 radio board. The main layout design concepts are shown with this reference layout to demonstrate the basic principles. Although these rules will be shown through a design that uses a 4-element matching, similar design practices should be applied with a 2-element matching network as well. For low-power applications below 13 dBm, a 2-element LC network is sufficient, while high-power solutions above 13 dBm require a 4-element match. The reference schematics and layout designs of the matching networks are usually provided by the manufacturer of the RFIC. It is recommended to copy the entire RF area from a reference design as is. Of course, it is not always possible due to size restrictions, different form factors, etc. Thus, a custom design may need to deviate from the reference one. Although the size of a matching network is relatively small, due to the high frequency, the matching is sensitive to the physical parameters of the matching layout, besides component values, of course. Compared to a reference layout design, different component distances and trace lengths introduce different parasitic inductances. Different substrate thickness, dielectric constant and gaps between traces introduce different parasitic capacitances. Different component distance, orientation, relative orientation introduce different coupling between components. Different component types, sizes introduce different component parasitics. This can cause detuning of the reference matching or filtering and/or detuning of the load of the RF crystal. The possible effects can be decreased TX output power of the fundamental, decreased RX sensitivity, increased spurious emission levels, increased current consumption, frequency offset between different boards. All these mentioned effects can be offset both with conducted and radiated measurements. From RF radiation point of view, the whole PCB should be considered as a system. So not only the design of the RF area, but in most cases the layout of the entire PCB can affect the radiated performance. Practically, in case of an incorrect RF module layout design, the radiated spectrum can have lower fundamental and higher harmonics or spurs compared to the values expected based on the conducted output spectrum and the gain of the used antenna. Incorrect layout can cause the radiated spurs to violate the relevant EMC regulation even if the conducted spectrum they are below the limit with nice margins. Although in most cases the reference designs are not complete applications, the RF layout design principles introduced on them should be applied for the whole PCB area containing the RF section or module. If copying the reference layout design is not possible, the layout design recommendations shown in the next slides should be applied. The first component of the matching network should be placed as close to the 2G4 RF IOP pin of the RFIC as possible to reduce the series parasitic inductance and to avoid any detuning effects. The neighboring matching network components should be placed as close to each other as possible to minimize any PCB parasitic capacitance to the ground and the series parasitic inductances between the components. Use the same or near the same trace width for connecting the components to each other as the pad width. It is typically 20 mm in case of using 0402 sized SMD components. The widened connections are necessary to reduce series parasitic inductance between components. The lowest value bypass capacitors filter on frequencies around the fundamental. This way they have to be placed close to the VDD pins and need good grounding with many close vias at the ground side. The capacitor with the value around the 100 nanofarad filters the several tens of megahertz frequency range, thus the leaking clock spurs. Filtering these spurs is important as they can be upconverted inside the chip, causing unwanted spurs at several 10 MHz offset around the carrier. The largest value capacitor filters the several 100 kHz interferences typically coming from a switching power supply. It can be placed far away from the VDD pins and is not required in case of battery operation. VDD filtering capacitors should be placed close to the VDD pins. The smallest value one should be the closest. The crystal should be placed as close to the RFIC as possible to ensure that wire parasitic capacitances are kept as low as possible. This will reduce any frequency offsets. Avoid leading supply traces close or beneath the crystal or parallel with a crystal signal or clock trace. Use similar topology for all boards in the communication system. Connect the crystal case to the ground using many vias to avoid radiation of the ungrounded parts. Do not leave any metal unconnected and floating that may be an unwanted radiator. Use an isolating ground metal between the crystal and VDD traces to avoid any detuning effects on the crystal caused by the nearby power supply and to avoid the leakage of the crystal or clock signal and its harmonics to the supply lines. The grounding effect in the thermal straps used with capacitors should be improved. In addition, the trace near the GND pin of these capacitors should be thickened. This will minimize series parasitic inductance between the ground pure and the GND pins. Additional vias placed close to the GND pin of the capacitors, thus connecting it to the bottom or inner layer GND plane, will further help reduce these effects. The reason for not using vias on the entire GND section is due to the restrictions of the actual radio board design. These restrictions include traces routed on other layers or components on the bottom side, which are not shown in this slide. The exposed pad footprint for the pedal of the EFR32 IC should use as many vias as possible to ensure good grounding and heat sink capability. In the reference designs, there are 25 vias for the 7x7 mm sized package ICs, each with 10 mm diameter. The pedal ground should also be connected to the top layer GND metal if possible, to further improve RF grounding. This may be accomplished with diagonal trace connections through the corners of the EFR32 IC footprint. Coupling through the ground can occur between the nearby filtering capacitors, especially at high harmonics, which can decrease the effectiveness of the low-pass filtering and can cause higher harmonics that can be observed both conducted and radiated. To avoid the possible high harmonic levels, it is recommended to connect the nearby filtering capacitors to the ground planes on different sides of the transmission line. Use at least 0.5 mm separation between traces or pads to the adjacent GND pores in the area of the matching network. This technique will minimize the parasitic capacitance and reduce the detuning effects. The area under the RF chip and the matching network. In case of 4-layer PCBs, this is the first inner layer beneath the top layer, should be filled with continuous ground metal, as it will show good ground reference for the matching network and will ensure a good low impedance return path to the RF chip's ground as well. Board routing and wiring should not be placed in this region to prevent coupling effects with the matching network. It is also recommended that the GND return path between the GND vias of the TX or RX matching network and the GND vias of the RFIC pedal should not be blocked in any way. The return currents should see a clear, unhindered pathway through the GND plane to the back of the RFIC. Use 50 ohm grounded coplanar lines where possible for connecting the antenna or the UFL connector to the matching to reduce sensitivity to PCB thickness variation. This will also reduce radiation and coupling effects. Use many GND vias near the coplanar lines in order to further reduce radiation. To achieve good RF ground on the layout, it is recommended to add large, continuous GND metallization around the area of the RF section at a minimum. Better performance may be obtained if this is applied to the entire PCB. To provide a good RF ground, the RF voltage potentials should be equal along the entire GND area, as this helps maintain good VDD filtering and also provides a good ground plane for the monopole type antennas. Gaps should ideally be filled with GND metal, and the resulting sections on the top and bottom layers should be connected with as many vias as possible. Use as many grounding vias at the GND metal edges, especially at the edge of the PCB and along the VDD traces as possible in order to reduce their harmonic radiation caused by the fringing field. In a design with more than 2 layers, all of the wires or traces should be placed in one of the inner layers, especially the VDD trace. Also avoid putting it close to the edge of the PCB. The whole top and bottom layers should contain as much continuous GND metallization as possible to reduce the radiations of the traces. In the last section, I am going to show a layout where the previous recommendations seem to be more or less implemented, but still there are minor mistakes in the design. Those can cause detuning of the fundamental frequency, lower power level, higher current consumption and higher harmonic power level as well. The problems with this design will be shown step by step. First of all, the first matching component, L1, should be placed as close to the 2G4 RF IOP pin as possible in order to reduce the series parasitic inductance, which can detune the output impedance from the optimal 50 ohm. The crystal should be placed as close to the RFIC as possible to ensure that wire parasitic capacitances are kept as low as possible. This will reduce any frequency offsets. Use the same or near the same width traces for connecting the components to each other as the component width. It is typically 20 mm in case of using SMD0402 components. Connect the first C1 and second C2 filtering capacitor to the ground planes on different sides of the transmission line to avoid the possible high-frequency harmonic leakage through the ground plane. The ground pin of the picofarad valued PA-VDD filtering capacitor does not have any GND via. This way it is connected to an isolated metal with no ground connection. Use an isolating ground metal between the crystal and the VDD traces to avoid any detuning effects on the crystal caused by the nearby power supply and to avoid the leakage of the crystal or clock signal and its harmonics to the supply lines. Use at least 0.5 mm separation between traces or pads to the adjacent GND ports in the area of the matching network in order to minimize the parasitic capacitance and reduce the detuning effects. Check the datasheet of the use part for the design recommendations. Further details on proper RF layout design can be found in AEN 928 EFR32 Layout Design Guide application note. Thank you for watching.